Ladies and gentlemen, welcome to a new lecture in Calculus 1. So this would be the sixth lecture, and in this sixth lecture, we will talk about the algebraic computation of limits. We will see some basic properties of limits and how to compute them. So we will talk about how to add two limits, how to deal with the product of two limits with the quotient and so on, and powers and etc. All right, so let's get started. First, let me start with something basic. And well, so today we'll talk about algebraic computation. Of limits. All right. Okay, so let's start with some basic rules at first. So basic properties. So the first thing we need to start with is basic properties and rules for limits. Okay. All right. So let's start with this. Okay. And the first, before we start, for any real constant, let's say C, real constant C, right? Suppose that the functions f and g both have limits at the point C, at x equals C. So this is our assumption. So we suppose this. Okay, now the first thing we are going to talk about will be what we call the constant rule. And you will see that in this case, we would like to see what happens to the limit when we deal with a constant. And in fact, we'll have the following. This will be the lim as x approaches this constant C of, let's say, of k. As you can see, I have a constant here. This is nothing else than just k. As you can see, the quantity inside the limit, it has nothing to do with x. So it's just a constant. So the limit will be a constant. And this is for any constant. Okay. And let's represent this graphically. I want you to see exactly how graphically this looks like. And you will see that graphically this looks like this. Let me just show it to you. So I will have here, let's say, this line k. So this would be f of x equals k. This will be parallel to the x-axis. So, and let's suppose I have the point here. So this is the point of coordinate C, k, right? See, it's here. K is here. So this is, and as you can see, the limit goes from here, from the left, from the right. So it will be k, right? For example, to be more specific, let's say I have f of x equals 5, right? So I have a constant function 5, and we'd like to see what is the limit. So we would like to find the limit as x approaches 9, let's say, of f of x. Well, as we previously said above, this will be nothing else than just the limit as x approaches 9 since f of x is a constant function 5 of 5. And just look at the rule above. This is has nothing to do with this, so this is just the constant 5. Right? Let me box this. So this is it's very natural. It's common sense, I would say. Okay, now let's move to the second one. For example, when I have the identity function, and let me denote this. So this was constant rule. I will say limit of x rule. So in this case, I'll have the identity function. And what do I mean by that is the following is, I mean that the limit as x approaches c of the function x is nothing else than just c, the constant c. And we can represent this graphically. This function x is nothing else than just a line. Let me do it here. I think we have plenty of room. Oops. Oh, anyway, this is just a line that which will cross through the origin, right? And I'll have here the point, let's say, c and c, right? This is my function f of x equals x, right? Okay. All right, so this is what, and let's give an example, a quick example, is what if we take f of x to be x, right? And we want to find the limit as x approaches 5 of f of x. Well, this is nothing else than just the limit as x approaches 5 of x. And as you can see above, this is nothing else than just 5. We replace x by 5. Okay. Now, what if we have constant multiple rule? Okay, multiple by a constant rule, let's call this anyway. Well, here we'll have the following is the lim. So in other words, it will be similar to the previous one, but in this case, the only difference is that here I'll have a constant. So I have a constant k times my function f of x. So the k will not influence too much the limit, so we'll take it out. So it will be k times the limit as x approaches c of f of x. For any constant k. Okay, and an example here will be the following. Let's evaluate the following limit. Let's say we have lim as x approaches -2 of 5 times x squared plus x minus 2 over x plus 2, right? Well, as you can see here, I have this 5. Look at it. So maybe I should take it out. So this would be equal to, it will be equal to, so like I said, we take the 5 out, so it will be 5 times the lim as x approaches -2 of x squared plus x minus 2, everything over x plus 2. Right? And anyway, this will be, and I'll this will be, and I'll skip the details, but I'll get back to this example. In fact, we did this because we factored it. In fact, let's do it again. So this was, if I remember correctly, it was -3. So this guy here, it was equal to -3. We've done this in the previous lecture. We factored x squared plus x minus 2 as x plus 2 times x minus 1, and we cancel x plus 2, and as x approaches -2, will approach -2 minus 1, which will be -3. So this will be 5 times -3, and this will be -15. Okay. And now let's see what happens when we have the sum of two functions. So let's call this a sum rule. And in this case, again, it's pretty simple. We have that the limit as x approaches c of f of x plus g of x. So we add these two functions, and this will be nothing else than just the limit as x approaches c of f of x plus the limit as x approaches c of g of x. Right? That's the sum rule, as you might expect. And now let's see an example here. An example, let's evaluate the following limit. Evaluate the limit as x approaches, again, let's take x approaches -2, and we'll take the same expression, x squared plus x minus 2 over x plus 2, and plus x plus 2 over x plus 2. Let's suppose we have this expression. Well, this is nothing else. By the sum rule, this will be equal to the limit as x approaches -2 of x squared plus x minus 2, everything over x plus 2, plus the limit as x approaches -2 of x plus 2 over x plus 2. Right? You can see I have the sum. This is this guy here. Imagine that this guy here is like an f of x, and this guy here is like a g of x. And I have, right? And by applying the sum rule, here I apply the sum rule, I'll get this. Well, we have seen previously, well, that this limit, so this would be -3 plus the limit as x approaches -2 of x plus 2 over x plus 2. But this guy, by the way, pay attention here, we discussed this in the previous lecture, try to simplify the computations as much as possible. Don't plug in x equals -2 at this point, because this will simplify with this, and this will be nothing else than just 1. So it will be -3 plus 1, which is -2. Right? Because if you plug in x equals -2 in that fraction, it will give you 0 over 0, which is indeterminate. Because we have established, and I think I told you about this indeterminate, and you will see about others as well. And the very first lecture when we talked about the big picture of calculus. Okay. Well, as we have the sum rule, well, probably as you can guess, we also have the difference rule, because the difference is nothing other than just the sum. So the difference rule is the following: is the limit as x approaches c of f of x minus g of x, and this will be the limit as x approaches c of f of x minus a limit as x approaches c of g of x. Okay, that's the rule. And now let's see an example. Again, example would be along the same, along similar lines with the previous one. So let's evaluate the limit as x approaches -2 of, let's consider this x squared plus x minus 2 over x plus 2. Again, I have this minus x plus 2 over x plus 2. So it's again the same thing. So by the difference rule, this would be equal to, so here I apply the difference rule. So this will be the lim as x approaches -2 of x squared plus x minus 2 over x plus 2 minus the lim as x approaches -2 of x plus 2 over x plus 2. Well, as we previously have seen, this is -3 minus 1, which will give us -4, right? And now, 6, the product rule. Well, again, this will fit to your expectations. This will be lim as x approaches c of f of x times g of x. And this is nothing else than just the product of the limit of the product is the product of the limits, as you might expect. So this is the lim as x approaches c of f of x times the lim as x approaches c of g of x. All right, that's the rule. And now let's see an example. Let's see something similar. So this is lim. We evaluate. We like to evaluate the lim as x approaches -2 of x times x squared plus x minus 2 over x plus 2. So again, by the product rule, so by applying the product rule, this would be equal to the lim as x approaches -2 of x times the limit as x approaches -2 of x squared plus x minus 2 over x plus 2. Well, the first limit, if you plug it in, it will give you negative. So by applying you see, the limit of x rule, the second rule, so it will give us -2 times, and as you remember, so this is -2 here, and this guy, as we have previously said, is -3. So it will be -2 times -3, which is 6. All right, that's beautiful. And now, 7 rule, quotient rule. Is the following. It's similar to a product, but we're going to multiply by the inverse of by 1 over g. So we will have that lim as x approaches c of f of x over g of x. So the limit of this quotient will be nothing else than just the limit as x approaches c of f of x over the limit as x approaches c of g of x. If the limit, we have to take something into account of as x approaches c of g of x is different than 0. So provided we have that, then the limit of the quotient is the quotient of the limits. Okay. Let's see an example. Let's evaluate lim limit as x approaches -2 of x squared plus x minus 2 over x. Okay, you see I have the quotient of two functions here. So by applying the quotient rule, this will be nothing else than just the limit as x approaches -2 of x squared plus x minus 2 over lim as x approaches -2 of x. And this will be equal to, well, you can plug it in. The first one will give us, if you plug it in, it will be -2 squared plus -2 minus 2, everything over -2, which will give us 4 minus, so it will be 0 over -2, so this will be 0. That's it. And now we also have the power rule, which says the following. This rule says that the limit as x approaches c of f of x, and let's raise this to some power, let's say to n. This will be nothing else than just the limit as x approaches c of f of x raised to the power n. And let's say a few words about this n, where n is a rational number and the limit on the right exists, provided this. If this happens, then indeed we have this power rule. All right, let's see an example, a very easy example. The limit as x approaches, let's say 3 of x cubed. Well, this is nothing else than just the limit as x approaches 3 of x, everything cubed, and by applying the x rule, this will be nothing else than just 3 cubed, because this guy here inside, the limit of this is 3, so it will be 27, and that's it. All right. Okay, so these are the basic rules. As you can see, 8 of them. I believe they're quite easy. It's very easy to operate with them. Now, I want to see if we have some kind of a polynomial function. I want to see something a little bit more complicated to see how do we operate with this. So the question we want to answer, based on everything that we have seen so far, is the following. How do we find the limit of a polynomial function? That is a question we want to answer, right? And for example, let me give you an example. In fact, let's start with an example, and then we'll say a few words about how about the general method of finding the limit of a polynomial function. And the example I have in mind is the following: is to evaluate the lim as x approaches, let's say 2 of, and let's take here 2x to the 5th minus 9x cubed plus 3x squared minus 11. Okay, so let's take a polynomial function of degree 5. Well, as you can see here, I have plenty of functions, but I can apply all the operations above at once, all of them at once, and we'll have the following. So this will be equal to the lim as x approach, in fact, not at once, let's do it step by step. It will be 2x to the 5th minus the lim as x approaches 2 of 9x cubed, right? Plus the limit as x approaches 2 of 3x squared minus the limit as x approaches 2 of 11. Okay. Now, as you can see, we have the constants, so we'll take them outside the limit. So this will be 2 times the limit as x approaches 2 of x to the 5th, right? Minus 9 times lim as x approaches 2 of x cubed plus 3 times lim as x approaches 2 of x squared minus, and the limit of this will be 11. So let's write this, right? Because here we apply the constant rule. All right, so we apply the multiple by a constant rule. Now we have some powers here, so let's apply the power rule, right? And this would be 2 times the lim as x approaches 2 of x, everything to the power 5th, minus 9 times lim as x approaches 2 of x, everything cubed, plus 3 times the limit as x approaches the 2 of x, everything squared, minus 11. Well, at this point, so here we apply the power rule. So now let's just, so it will be 2 times 2 to the 5th minus 9 times 2 cubed plus 3 times x plus 2 squared minus 11. And if we do all these computations here, so it will be 64 minus 72 plus 12 minus 11. And this will give us -7. Okay, whatever. So now you have seen an example. So it's pretty, as you can see, it's the way you would expect this. So pretty straightforward. Well, now let's talk about the limit of a polynomial function. If P is a polynomial function, then, well, guess what happens? The limit as x approaches c of, let's say, p of x, where p of x is the polynomial functions that I mentioned, is nothing else than just p evaluated at c. That's it. And the previous example, the example above, illustrates that perfectly. And let me point out the remark so that things are clearer. If f is any polynomial, right, then the limit at x equals c can be found by substituting x equals c into the formula for f of x. So that's how we find it. Well, right? Okay. Now let's see another example. I don't remember the number, but anyway, it doesn't really matter. So we want to evaluate the limit as, let's say, y approaches -1, and we'll take the following fraction. So this will be y cubed minus 3y plus 7, or everything over 5y squared plus 9y plus 6. Right? Well, as you can see here, we have the quotient of two polynomial functions, right? So this is the quotient of two polynomial functions. So it would be a good idea to apply the quotient rule. So we have that the limit as y approaches -1, right? Of y cubed minus 3y plus 7 over 5y squared plus 9y plus 6. So this would be, by the quotient rule, let me say it specifically here, quotient rule. By the way, this is a Q here, it's not a G or a 9 or whatever. This will be the limit as x approaches -1 of y cubed minus 3y plus 7, everything over the limit as x approaches -1 of 5y squared plus 9y plus 6. Okay, so I apply the quotient rule here. Now it's time for me to replace y equals -1 in each fraction. Let's see on the top, what do we have? So we will have what? So this would be, let's write it here below. This will be the -1 everything cubed minus 3 times -1 plus 7. Everything over 5 times -1 everything squared plus 9 times -1 plus 6. And this will be, after some computations, it will give us 9/2. So that's the value of the limit, right? So it was pretty straightforward. It was nothing else than just applying, well, I skipped a bunch of rules. Well, I applied the power rule and multiple by a constant rule, the y rule, whatever. But it's quite clear at this point that how we can operate with these polynomial functions. Okay, now I want to point out the following remark. Well, if the denominator of the rational function is not 0, and I want you to pay attention here because it's very important, right? If it's not 0, the limit of the denominator can be found by substitution. Right? If the limit of the denominator is 0, well, we find ourselves dividing by 0. In fact, let me dividing by 0, which is not quite okay. We'll see later on why this is not okay. It is not okay. All right, I will explain later on what this is all about, because this will deal with some kind of infinite limits. And in fact, let's explain it now. So we will talk about infinite limits. fact, I will draw some pictures, but before that, let me say that a function f that increases, and we have seen what increasing mean or decreasing means, or decreases without bound as x approaches c is said to tend to infinity, and I will denote infinity by this symbol. This is a symbol for infinity. Let's see. Right, this is what I mean. This is a symbol for infinity. Okay. Let's indicate we write this in the following way. And I'll show you how we write this. So we will write this as lim as x approaches this constant c of f of x. And this will be infinity. So we're going to write it in this way, right? If f increases without bound, right? And we're going to write the lim equals negative infinity if f decreases without a bound. Right? This is how we're gonna write. All right, let me draw some pictures so that you will see it better how we write this, how we illustrate this, these two facts here. So let me draw the following pictures. So I will draw for the first one when the limit is positive infinity. Let's say. Let me put here a positive infinity so that things are even. So this is positive infinity in the first one, and the second one is negative infinity. So let me draw the picture. So we have the following two pictures for positive infinity. So let's suppose we have something like this. So here I have, so this will be a vertical asymptote. This guy is a vertical asymptote. Right? Let's say C, and the function will go like this. This is x, this is y, right? F of x will go like this. Right? And this way we can illustrate that it goes up and it doesn't stop. So it goes, this is the, as x approach, this means that this illustrates that the limit as x approaches, as you can see, as x approaches the constant c of f of x, this will be positive infinity. Or this is coming from the left, but you can come also from the right. So you can also go like this, for example. We draw with another color. You can also come like this, right? It's the same thing. All right, this is for the first scenario when the function increases without a bound, as you can see, it increases and it doesn't stop. So that's, we can write this by saying that the limit as x approaches c, as you can look in the picture, x approaches c because the line is getting close. The function f of x, its graph is getting very, very close to this vertical asymptote, C. So all the points, x are very close to C, but f of x goes and doesn't stop. So it grows without a bound. So we can say that this means that the limit as x approaches C of f of x is positive infinity. And now for the second case, we have the following picture. Let's draw here. And again, we have this vertical asymptote, let's say here. So this is, again, x equals C. And let's say I have a function that goes like this. Right? And let's say I have another one that goes like this. Right? As you can see, I can illustrate this, that this function, they decrease without a bound. So they go down to negative infinity. We can illustrate this by saying that the limit as x approaches C of f of x is nothing else than just negative infinity. Right? Anyway, I think it's quite clear. The two pictures are quite clear, right? As you can see in the first one, it increases without and doesn't stop. So the limit will be positive infinity. And in the second picture, they decrease, they don't stop. So the limit is negative infinity. Well, let's see an example. And the example I have in mind, and we'll also draw a picture for this, is the following. Let's evaluate the limit as x approaches 0. This will be a little bit delicate, but anyway, of 1 over x squared. So we want to evaluate this limit. So let's look at it. And let's see, what should we say about this limit? Well, as you can see here, if we look closely at this, well, let's draw a graph. Let's see graphically what happens to this function. And then we'll see the details. So let's draw the graph of this function. And the graph will look like this. Ouch. Okay. Well, not quite like this. Okay, let me draw it again. Okay. All right. So this is how the graph will look like. Well, this is the graph of, so we can say that the graph of f of x equals 1 over x squared. We say that this rises, okay, we can say that, without a bound. As x approaches 0, right? It's quite clear that it rises. Right? Well, let's see. But you see here, I have this, it's coming from the left and also it's coming from the right. So let's write this down. So we will have that the limit as x approaches 0 from the left of f of x, right? It will be infinity, right? in fact, let me explain it a bit more. This will be 1 over 0 minus squared, right? Which will be infinity. And the limit as x approaches 0 from the right of f of x will be 1 over 0 plus squared, again, which will be infinity. So we say that this function diverges. That the function diverges. When I say that diverges, I mean there is no bound. That's what I mean. Okay, so we can say that the limit as x approaches 0, let's say, of f of x, well, does not exist. So it's important to remember that this guy infinity is not quite a number, but anyway, well, it's more like a symbol which represents the unrestricted growth in the magnitude of the function. That's how we should understand this number. All right. Now let's see another example. So let's see an exercise more likely. And now let's evaluate some functions and, for example, evaluate the limit as x approaches, let's say, -2 of the cube root, as you can see, of, let's put here a polynomial function, a quadratic function, in fact, x squared minus 3x minus 2. All right, so let's look at this and let's try to evaluate it. Well, so we have that the limit as x approaches -2 of the cube root of x squared minus 3x minus 2 will be nothing else than the limit as x approaches -2 of x squared minus 3x minus 2, and everything to the power 1 over 3. Again, by applying the power rule, right? This will be nothing else than just the limit as x approaches -2 of x squared minus 3x minus 2, and everything to the power 1/3. And now we're just going to plug in, so this would be -2 squared minus 3 times -2 minus 2, everything to the power 1/3, and this would be, after some computation, will be equal to 2. Let's see exercise 1. Let's see now exercise 2. Let's see, we are interested how the main trigonometric functions behave at x equals 0. So given that well, it's quite easy to see that the limit as x approaches 0 of sine of x is 0, and the limit as x approaches 0 of cosine of x equals 1. Evaluate the limit as x approaches 0 of sine squared of x, and the limit as x approaches 0 of 1 minus cosine of x. Well, let's look at this. Let's just basically, we just apply the power rule. So by the power rule, we have that the lim as x approaches 0 of sine squared of x is nothing else than just the limit as x approaches 0 of sine of x, everything squared. But we know that this is 0, so it will be 0 squared, which is 0. Also, the limit as x approaches 0 of 1 minus cosine of x will be by the applying the difference rule. If I apply the difference rule, this will be nothing else than just the limit as x approaches 0 of 1 minus the lim as x approaches 0 of cosine of x. So the first one is 1 minus the limit of as x approaches 0 of cosine of x, which is 1. So this will be 0. Well, pretty simple, right? So, and now let me tell you something about the limit of trigonometric functions. A few things. Well, limits of trigonometric functions. And well, as you might expect now, we have the following. That the limit as x approaches, let's say, okay, let me say something first. If c is any number, any real number in the domain of a given function, then we have the following. Let me read. The lim as x approaches c of, and let's say here, I'll put this trigonometric of x will be trigonometric of c. That's what you need to know. Where trigonometric are the following. Trigonometric of x is the following, belongs to the following set. So cosine of x, sine of x, tangent of x, cotangent of x, secant of x, and cosecant of x. So any function, any of these functions, you plug it in, it will give you the value of the function at c. All right, so you expected this to happen. But also we have some other things going on here, some special limits that they're very, very useful. In fact, they're very important. Well, and I'm going to give them without a proof, which are the following. The limit as h, the first one is that the limit as h approaches 0 of sine of h over h is 1. This is always true. Keep this in mind. And also the second one, I'm going to write it here. The limit as h approaches 0 of cosine of h minus 1, everything over h. So this guy will be 0. Keep this in mind as well. So these two, I want you to look at them. They're very, very important. And we'll see how we apply them in an application. All right, now let's see some other exercises. So exercise, I don't remember what number is. Exercise 3 says the following. Let me evaluate the following limits. And I would like to explain this. The following limit. This is lim as x approaches 2 of x squared plus x minus 6, everything over x minus 2. Okay. As you can see here, I have a fraction, right? The top is a quadratic function, the bottom is a linear function. Both of them are polynomial functions. Like I said, of degree 2 and degree 1. And now let's see what happens. So let's try first to apply the quotient rule. So this will be equal to, and let's write here by the quotient rule. So by the quotient rule, this will be nothing else than just the limit as x approaches 2 of x squared plus x minus 6 over lim as x approaches 2 of x minus 2. And now let's compute each limit of this. So this will give us, if you plug it in, it will be 2 squared plus 2 minus 6 over 2 minus 2. And this will give us 0 over 0. Oh my goodness. This guy is 0 over 0. In fact, let me write it like this. 0 over 0, it's one of the indeterminates, so this is undefined. I want you to pay attention. Always, when you get 0 over 0, then it's undefined. So the quotient rule doesn't work in this case. So we need to come up with something else, maybe something smarter. Well, what is the main impediment here? What is the main problem? The main obstruction that doesn't allow us to get the limit? Well, if you look, maybe since I have a fraction, maybe I could get rid of, maybe I could simplify it a bit more. Maybe I could make it look like something nicer. Maybe instead of that fraction, maybe I won't have a fraction. Well, and if you look even closer, since I have the quantity on the top has degree 2 and the quantity on the bottom has degree 1, maybe I could think of writing the quantity on the top in terms of the quantity on the bottom. So maybe I could do this. So maybe I should, let's do something. Well, maybe we can factor this guy on the top, x squared plus x minus 6. So let's do that. So we have that the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. This guy, we can factor the top. This will be the limit as x approaches 2 of, and now we can factor this guy, and we can factor is as x minus 2 times x plus 3. Everything over x minus 2. Wow, that's beautiful. These two go away. So finally, I can write this in a simplified way as the limit as x approaches 2 of x plus 3. And this will be equal to, if you plug in x equals 2, will be 2 plus 3, which is 5. Wow, that's great. Well, the reduction, the simplification is valid as long as x is not 2, but x approaches 2, but is not equal to 2. So won't have any problem. All right, let's do much more examples of this type, because I want you to get the main idea. And the other example that I have in mind is the following. If we want to evaluate the limit as x approaches 4, right, of the square root of x minus 2 over x minus 4. Again, by direct computation or just applying by the quotient rule, we have that the limit as x approaches 4 or square root of x minus 2 over x minus 4 will be, well, lim as x approaches 4 of square root of x minus 2 over a lim as x approaches 4 of x minus 4 equals, so it will give us 0 over 0 again, which is undefined. Wow. So again, applying directly the quotient rule doesn't give me anything. So again, this is what you need to do always. You need to apply whatever, the product rule, the quotient rule in this case, so that you can get 0 over 0. And then once you get 0 over 0, then you need to come up with something else. Well, since well, I assume that as a prerequisite for this course is college algebra, which I assume that you all know. Let's do something to this fraction. What can we do to this? That is the question. Can we do something to this? And in fact, let me write it in this way. Maybe you can see it. The square root of x minus 2 over x minus 4. Can we write this in a certain way? Maybe I can multiply by the conjugate, right? So the conjugate of the square root of x minus 2, it will be the square root of x plus 2. And this will be the square root of x minus 2 times, so basically I'm multiplying on the top and on the bottom by the conjugate of x of square root of x minus 2, which is square root of x plus 2. So this will be this guy. And now if we do this computations here, this will be nothing else than just x minus 4 over square root of x plus 2 times x minus 4. Wow, actually it cancels. Look at this. This is nothing else than just 1 over square root of x plus 2. Wow, that's really nice. So we got this. So here we multiply. Always when you have radicals, you multiply by the conjugate. Always. Okay. Right? And since we do this, it follows that the limit as x approaches 4 of the square root of x minus 2 over x minus 4 is nothing else than just the lim as x approaches 4 of 1 over square root of x plus 2. And now we can plug it in, so it will be 1 over square root of 4 plus 2, which will give us 1 over 4. And that's it. Right? Keep in mind, always when you deal with radicals, think about the conjugate. When you deal with radicals and you get, once you apply any rule and you get something that is undefined, you think of the conjugate. All right, now let's do another exercise 5. Which says the following. Let's consider a piecewise function. Let f of x be the following function: x plus 1 if x is positive, and x squared plus 1 if x is negative. And now the question is, find the limit as x approaches 0 of f of x. So what is this? Well, keep in mind, if we look at the function, is not defined at 0. So let's notice this. The function f is not defined at x equals 0. Well, and as you can see, the function f is defined differently on each side of the 0. So for 0, for the positive, is defined as a linear function, and for the negative is defined as a quadratic function. So let's see. So what we should do is that we need to check that, let's write this, and we need to check that maybe I should say whether the left hand limit is the same as the right hand limit. In other words, let's do this. The left-hand limit will be lim as x approaches 0 minus of f of x. And keep in mind that this f of x is nothing else than just, well, let's look for what values x is negative. We have x squared plus 1, so this will be the limit as x approaches 0 from the left of x squared plus 1, which will give us 1. And the limit as x approaches 0 from the right of f of x, it will be nothing else than just limit as x approaches 0 plus, and f of x in this case will be x plus 1, and this will be 1. So as you can see, both these two limits are equal, right? The left-hand limit and the right-hand limit are equal. So from here, this implies that lim as x approaches 0 of f of x is 1, right? Okay, and in fact, we can actually see this graphically. Let's see graphically what's going on. And let's draw the picture. You will see it. In fact, you always draw a picture so that you can see it better. So graphically, so we'll have this point, so the limit here will be at this point 1. And here, let's say we have this this arc of parabola, but it keeps going. Let's say here, right? This is the graph of y equals x squared plus 1. And here we'll have a line which goes like this. This is the graph of y equals x plus 1. So as you can see here, in this case here, this is nothing else than just the limit as x approaches 0 from the right of f of x is 1. And here, I'll have that the limit as x approaches 0 from the left of f of x will be 1. So both of them agree. Well, another example is when, and let's see when they don't agree. And let's see exercise 6. Which says the following. Let's consider the following piecewise function, which is x plus 5. If x is positive, right? And x if x is negative. So again, we want to find the limit as x approaches 0 of f of x. Well, in this case, as we have seen in the previous example, the left-hand limit, let's say limit as x approaches 0 from the left of f of x, as you can see, is nothing else than just the limit as x approaches 0 from the left of x, which is 0, and the limit as x approaches x from the x approaches 0 from the right of f of x, it will be nothing else than just the limit as x approaches 0 plus of x plus 5, which will be 5. The two are not equal. So we can conclude that the limit, okay, let me write it in words, the limit as x approaches 0 of f of x does not exist. Let's see, let's interpret this graphically. Again, let's draw a picture. So we have here the axis, right? And for here I have this 0.5. Here I go like this. This will be the graph of y equals x plus 5. As you can see here, the limit as x approaches 0 from the right of f of x is 5. And now we will have that here. We will have, this is the graph of y equals x, right? This is the first bisector, but this time it will stop at 0. So this, we will have here that the limit as x approaches 0 from the left of f of x will be 0. As you can see, it doesn't look okay, so the limit does not exist, right? Okay, I think it's quite clear how we can operate with these. Now, let me see some other examples, some other tricky examples of limits. So let's see exercise number 7. And I think after this, we're going to stop here. There are more examples in the notes. Some of them are very easy. It's just, they're very straightforward. So I'm not going to, prefer not to waste any time with them. But this one, these two ones, I'm actually curious about these. So find the following limits. And the first one is the limit as x approaches 0 of sine of 3x, everything over 5x. And the second one is the limit, and in this time we will involve the inverse function, arc sine of x, everything over x. We want to find these two limits. All right, let's see the first one. Well, in the first one, if we plug in, so if we apply the quotient rule, so by the quotient rule, we have, what do we have? We have that the limit as x approaches 0 of sine of 3x over 5x. This will be the limit as x approaches 0 of sine of 3x everything over lim as x approaches 0 of 5x. Well, if we plug in, sine of 0 will be 0, so this will be 0 over 0. Again, it's undefined. So we don't want that. So we need to do something. We need to come up with something. All right. Remember, I gave you something about some special limits earlier in this lecture. Maybe we should do that. So we need to come up with something smarter. So what that might be? Well, we said it earlier. There was this special limit, which said that the limit as h approaches 0 of sine of h over h is 1. So let's use that. So we want to use that the limit as h approaches 0 of sine of h over h is 1. So let's see, how should we do that? How about well, a trick? Not the magic trick. I want to call it magic, but anyway. What I mean by trick is the following. So let's write this limit in the following way. The limit as x approaches 0 of sine of 3x over 5x And I'm going to write it in the following way. So this will be the lim as x approaches 0. And let me put here the constant 3/5 times sine of, let me divide and multiply by 3, sine of 3x over 3x. This is a constant, but it will go outside the limit. So this will be 3/5 times the limit as x approaches 0 of sine of 3x over 3x. But this guy here, this is 1. And this will be 3/5 times 1, which is 3/5. Why is this 1? Well, look at this guy here. You take h to be 3x. As h approaches 0, 3x will approach 0, and that's it. It's just that special limit for, instead of x, is 3x. Anyway, right? So that's it. And the second one, now let's do a substitution here. So we make the following substitution. And this substitution is arc sine of x, which is, by the way, let me remind you that this is sine to the -1, so it's the inverse, equals u. So I'm going to make this substitution. Let's do this one. All right. Okay. What does this imply? If we apply the function sine here, so this means that sine of arc sine of x is nothing else than sine of u. But sine of arc sine of x, we said that this is x. So x is sine of u. So x is sine of u. And now let's see the bounds. As x approaches 0, sine of u approaches 0. And this implies that u approaches 0. So now let's rewrite the limit. Thus, the limit as x approaches 0 of arc sine of x over x is nothing else, and now we write everything in the new variable. This will be the lim as u approaches 0 of arc sine of x is u, and x is nothing else than just sine of x, sine of u, sorry. Right? Okay. And this will be, if you want to write it in this way, it will be just the previous limit. This will be nothing else than just, if you want to write it in this way, the lim as the u approaches 0 of 1 over sine of u over u. But now by applying the quotient rule, this will be 1, the limit as u approaches 0 of 1, which is 1, over the lim as u approaches 0 of sine of u over u. But from the previous one, we know that this is 1. So this will be 1 over 1, which is 1. So the limit, the second limit is 1. Right? Okay, these are very important limits. We'll see more applications, as probably we'll do more once we have some review session before exams. I'll show you even much more difficult applications than this. Well, I think this is enough for today. Anyway, I'll stop here. So as you can see, I have a background here. This is the city of Pittsburgh, where I used to live for 6 years of my life. And in the back, you can, if you look here, this is the stadium where the Pittsburgh Steelers, the football team, Pittsburgh Steelers, play their game. All right, I'm going to stop here. Thank you very much.